So welcome, good morning, David. So today we have David Jones from the Instituto de Astrofísica de Canarias. And before he starts his seminar, I'm going to introduce him for those who do not know him. David obtained his PhD in 2011 at the University of Manchester. In 2008 and 2009, he was a support astronomer at the Isaac Newton Telescope in La Palma. After his PhD, then he got a postdoctoral fellowship from the European Southern Observatory, and that's when he moved to Chile, where he supported also the operations of the VLT at the Paranal Observatory. These fellowships are 4 years fellowship, so the first 3 years it has to be spent in either in Santiago or in Munich. In David's case, was in Santiago de Chile, but then he could choose the 4th year to move to another place, to another institute, and then he decided to join the newly established astronomy group at the University of Atacama in Copiapó. And then in 2014, he decided to go back or to return to La Palma with a postdoctoral position at the IAC, and that's where he has been since. So, David, thank you very much for giving the seminar today.
Thank you.
And whenever you're ready, you can start.
Great. So thank you very much for inviting me to give a talk. So I'm going to talk today mainly about a phase of binary stellar evolution known as the common envelope, and how we can begin to understand that a little bit using these beautiful objects known as planetary nebulae. So I've used this fairly flouncy title of binary star chrysalis, because you'll see that the common envelope is a little bit like a chrysalis, through to cosmic butterflies, which is a very popular moniker for planetary nebula. As you can see, they do look a little bit like butterflies in space. So the first, if I can change slide, there we go. The first thing that I have to do is make sure we're all on know what is a planetary nebula. So it's quite a misnomer, because they don't really have anything to do with planets, although planets might perhaps play a role in their formation. They are in fact ionized nebulae that form around evolved sun-like stars at their end of their lives. So when a sun-like star reaches the end of its life, it throws off its outer layers, its outer envelope, and then these outer layers are then ionized by the now exposed core, which becomes much hotter. So it ionizes this shell, and we see the shell as the planetary nebula. So they are the ionized outer layers of sun-like stars, which are thrown off at the end of their lives. And we have this canonical image, this textbook image of how these things form. So as a sun-like star reaches the end of its life on the asymptotic giant branch, it begins to exhaust all of its outer envelope in the form of a slow but very dense stellar wind. So this gets rid of maybe half a solar mass, up to a few solar masses of material from the outside, in the form of this slow, dense wind, which is sort of in this cartoon represented by the pinkish material outside. But then as the core becomes exposed, the core shrinks and heats up on the way to becoming a white dwarf. And at this stage, it begins to blow a much faster but much more tenuous wind. And the interaction between these two winds is kind of like a snowplow, with the fast wind sweeping up the slow wind into a fine but even denser shell, which is then perfect to be ionized, and has the perfect conditions to be ionized by the core, which is heating up on its way to become a white dwarf. And so it's great. It works. It reproduces a number of observed properties of planetary nebula, except the morphologies. How can you have roughly spherical winds from a roughly spherical star and begin to produce shapes like these, from very bipolar hourglass-like structures through to things which seem to be multipolar and have multiple ejection axes, or even two separate shells, one consecutive after the other, through to something even as spectacular as this object, which we will return to later in the talk, Fleming 1, where there seems to be episodic ejections in a polar direction, which also have some precession associated with them. a jet, which is bipolar and rotating and episodic. So let's take the sort of simplest of these extreme morphologies, an hourglass. So if we go back to our two wind model, a slow dense wind and a fast tenuous wind, you can begin to form these kind of structures if you could make one of those winds, let's say the slow dense wind, axisymmetric. If we can make it concentrated in a particular plane and less concentrated in the other, you can imagine it being like putting an elastic band around a balloon when you blow the balloon up. The region which is constrained by the elastic band does still expand, but expands much more slowly because it's restricted by the extra material there, by the extra elastic band, and is free to expand in the other directions. So how can we make that first wind, the dense wind, aspherical or axisymmetric? People considered rapid rotation. If you make a star spin, it's going to throw off more material in the plane in which it is spinning than in the polar directions. It turns out if you want to make enough material expelled in that plane rather than in the poles, that the star has to be rotating at above breakup velocity. So it would never get to that stage in its evolution. So that doesn't work. Then for a long time, people considered magnetic fields, and magnetic fields can shape fairly effectively the winds of evolved stars. The problem is that in doing the shaping, the magnetic field gets diluted. And so you need a very strong magnetic field and something to sustain it. And so a single star isn't capable of doing that on its own. The magnetic field imparts a little bit of axisymmetry and then gets diluted too much. So we're left with binarity. If the star, which is dying, which is throwing off its outer layers, has a companion, it can either directly shape the wind through some kind of interaction like the common envelope phase, which I'm going to talk about, or even by imparting angular momentum to maintain the magnetic field. So binarity is now the most popular explanation for this. And as I said, the strongest, or perhaps the most obvious way in which this can happen is through a phase of binary evolution known as the common envelope phase, which is key in the formation of almost all, or if not all, evolved compact binary stars. So to try and explain this, I'm going to use this cartoon diagram here. So here in my cartoon binary, I have two main sequence stars, one more massive than the other. So the more massive star is on the right and is slightly larger. And the dashed line that encloses them is something which is known as the Roche lobe. So this is the smallest surface of gravitational equipotential, which includes both stars, which is a very fancy way of saying everything inside the dashed line on the left is probably gravitationally bound to the star on the left. Everything that's inside the dashed line on the right is probably bound to the star on the right. And anything that's outside of this figure of 8 is either bound to the system as a whole rather than to one or the other star, or is unbound completely. Okay, so as the stars evolve, the more massive star evolves more quickly. And as it ascends the red giant branch, it begins to swell. It grows in size. And if the two stars are close enough together, there is a chance that as the star grows, it will grow so big that it actually fills this surface of gravitational equipotential. And at that point, it will begin to transfer material through the point in the center, through the point where the two lobes cross, onto its companion. The star can then respond in one of two ways, depending on the structure of its outer envelope, basically depending on its evolutionary state. It can either shrink back, having lost material, it will shrink back and stop transferring material, or it can expand even faster. And if it expands even faster, then it will begin transferring material onto faster and faster and faster and faster in a runaway process until it eventually fills as well the lobe, the Roche lobe of the companion, at which point there's nowhere else for any more material to go except outside of the Roche lobe. So the material that's lost beyond then, the material that is then lost from the more massive star due to its continued expansion, then engulfs the whole system So this material is now no longer bound to one star or the other. It's only attached to the system. And importantly, it is not co-rotating with the two stars. So all the while, these two stars are orbiting one another. And this material is not in co-rotation. So there are friction forces. This friction transfers orbital energy and angular momentum from the binary to this material. And the end result being that the two stars spiral inwards, so their orbit shrinks. And because of the conservation of angular momentum, the envelope itself is ejected preferentially in the orbital plane. So the end result is the ejection of the envelope, just as would happen in a single star at the end of its life. But in this case, we've ejected almost all of it in the orbital plane, and we've made a very short period star at the center. So just to give another feel for this is a hydrodynamic simulation, state-of-the-art hydrodynamic simulation of this process, which is kind of looking top down. So we're going to see the orbital plane as if it was in the screen of your computers. And one thing that I want to highlight, because we'll come back to it again later, is that the beginning of this simulation places the companion, the secondary star, right on the edge of the giant star's envelope. Okay, so that's how we begin the simulation, basically artificially forcing the common envelope to begin. So if I start the simulation, you can see as the secondary, the companion, begins to interact with the primary's envelope, it starts to throw off this material in a sort of spiral structure into the orbital plane, and all the while the two stars begin circling one another closer and closer, reducing their orbital separation. So under this process, the orbital period of these stars will shrink from maybe a year or two down to only a day or less than a day. So it's really quite a dramatic change. And so the second thing that I want to point out about this simulation is that when it ends, the envelope has still not been completely removed. This is a problem for all hydrodynamic simulations of the process, that it's extremely difficult, unless you artificially input additional energy, it's very difficult to actually eject the envelope. And so these are the two things, the fact that we start by artificially forcing the common envelope to begin, and then that we don't successfully eject all of the envelope is something that I'm going to come back to later. Anyway, so you can see that the orbital separation has indeed increased, and we've ejected lots of material in a sort of spiral or ring shape into the orbital plane. And this is exactly what we see in post-common envelope planetary nebulae. So planetary nebulae that are formed through this process, generally or very frequently, have ring-like structures, or at least are bipolar, and have these density over contrasts in their wastes. And these are three examples where the central star, which looks like a single star but is actually so close together that it's unresolved for us, is a short, less than a day or around a day period post-common envelope binary. Great. So we've figured out that all of these bipolar planetary nebulae, or anything that's got an unusual or aspherical shape, must be from binary interactions. Fantastic. But then we have a problem. There are about 3,000 planetary nebulae in our galaxy, maybe 80% of which are aspherical, and probably a quarter of which are strongly bipolar or axisymmetric. And yet we only know of about 75 post-common envelope central stars. And 75 is not a quarter of 3,000. So what's going on? I'm going to try and tell you that that's not because they're not binaries, it's just that we haven't managed to find them yet. And to do that, I have to kind of explain how we identify these binary central stars. I've already told you that they're unresolved, they're point sources from the ground because they're so close together. So how can we tell that a point source is a binary star? If we're very lucky and the orbital plane is in the line of sight, then we'll see eclipses. That's very easy. But these stars are quite small, so the chance of finding things so close to the line of sight that we see eclipses is quite low. So we have to detect them via other means. We still do it using photometry, so by taking images just as you would to see an eclipse. But instead, we detect them as a result of the large temperature difference between the two stars. So as I mentioned earlier, the outcome of the common envelope phase is that we strip off the envelope of the star which goes on to form the planetary nebulae. And so it leaves behind its nucleus, which is evolving towards becoming a white dwarf. So it's contracting and heating, maybe has a temperature of up to, or maybe even above 100,000 Kelvin. And the companion is still a low mass main sequence star, so only a few thousand Kelvin. So it's a huge temperature difference. The end result being that because they are so close together, the side of the main sequence star, which is facing the pre-white dwarf or white dwarf, is being bombarded by radiation, becomes irradiated. And so here in this little cartoon, you can see 4 phases of this binary orbit of a star which is not of a binary star which is not orbiting in the plane in the line of sight. Instead, it's inclined a little, maybe 45 degrees. And you can see as it goes around its orbit, we see a different amount of this irradiated face, of this day face, if you want to consider it like that. So when we are at the conjunctions, we begin to see more or less of this irradiated face than when we do than we would at quadrature. So this gives a sort of characteristic shape to the variability of this of these sources as they go through the orbit. So seeing all of the day face, we see more light, and when we're seeing just the night face, we see less, and it sort of follows this sinusoidal pattern. So this is how we detect these systems for the most part, through this sinusoidal variability known as an irradiation effect. But the amplitude of this effect is a complicated function of the different parameters of the system. So you can imagine taking the inclination of the binary to start with. If we put that same system and have it orbit entirely in the plane of the sky, we won't see any variability, because no matter what phase of the orbit it's at, we will always see half of the day face and half of the night face of the companion. And slowly, as we increase the inclination towards being entirely in the line of sight, we see a stronger contrast, where at some phases we see almost entirely day face and some phases almost entirely night face. So the amplitude depends very strongly on the inclination. It also depends on the orbital period, which is equivalent to the separation of the two stars. You can imagine the longer the period, the larger the separation between the two stars, the less irradiating flux the companion intercepts, so the smaller the difference between the temperature of the day face and the night face. And then in terms of the type of companion star, it's less to do with its temperature, because even a quite hot main sequence star is still nowhere near the same temperature as a pre-white dwarf or white dwarf. It's more to do with the physical size. So at the same separation, an earlier type or more massive main sequence star is much larger, so intercepts much more irradiation, and so we see a much larger effect. So this is a diagram which sort of shows that a little bit. And on each of the plots, there's a horizontal red line, which is basically the detection limit of the OGLE survey, which has contributed about 1/3 of the known binaries. So you can see that there's, in that survey, which is the most complete survey that we've done to date, there's a significant number of systems that would have been missed. Anything over a few days orbital period, anything with an inclination of maybe less than 30 or 40 degrees, and anything with a low mass companion beyond about mid-M type. So that's one of the reasons why we're missing these systems. And more support for that hypothesis comes when we use a more sensitive instrument. If we go to space and look at, for example, data from the Kepler satellite, in the first Kepler field, there were 6 planetary nebulae observed, 5 of which provided useful data, and 4 of which were binaries. So extremely high hit rate, about 80%. And it's because these systems were from space, we're far more sensitive and not affected by the variations of the atmosphere, and so we can detect much lower level amplitude variability. And similar story if we look at other missions. If we extend to the K2 mission, which has observed a lot more planetary nebula, more than 100, from there we've already found 30 or 30 plus binary candidates which need a little bit more confirmation because of the reduced image quality of Kepler. TESS, from the first data release of TESS, there were 8 planetary nebulae that were observed with 2-minute cadence, and 7 of those were binary. So again, a huge, high fraction, low number statistics, but a high fraction. And that was work actually done by Alba Ayer at the CAB. And we hope that with the rest of the TESS data will be even more. And indeed, Gaia has already confirmed 4 new binaries and a lot more candidates, even though Gaia is not strictly a photometric variability survey. So there's hope that we'll be able to really show this missing population of low amplitude binaries. So the conclusion, what is the actual binary fraction if I said that 80% of planetary nebulae are spherical, and we want to try and explain those with binarity? Well, the fraction that's detectable photometrically from the ground is at least 20%. So that's a hard lower limit. That's from the Ogle survey, at least 20%. And we know that it's definitely higher than that because of the indications that we get from the space-based missions. And indeed, if we look at other indirect or more indirect or less harder methods to determine binarity, like infrared excess or radial velocities, which are very complicated with these stars, then perhaps the fraction is even as high as 80%, but the jury is still out on that. In any case, we can be certain that a significant number of planetary nebulae, perhaps most, are the result of a binary evolution, and that helps us explain their morphologies. Going beyond that, what more can we try and understand beyond just saying, okay, they're all binaries? Because I've shown you earlier that there's such a huge difference in all of the morphologies. There were some that were multipolar, there were some that were bipolar, some that had multiple shells. Well, go beyond that, we need to begin to characterize the properties. Rather than just show they're binaries, we have to understand what type of binaries or what their components are like. And so the first step to doing that is to try and derive the masses, the temperatures, the radii, and the inclination of the binary stars themselves. To do that, we need to take the observations that we used to confirm that they were binaries, the light curves, the variability in brightness as a phase of the orbit, and the radial velocity variability, and model those simultaneously to derive the parameters of the system. And just an indication of how challenging this is, particularly from the ground, on the left, I'm showing you 5 images of the same planetary nebula in different bands. And so you can imagine how difficult it is to get accurate photometry of the central star of this system, which is so clearly seen in the H-beta continuum, for example. It's the brightest thing in the middle of the field. When in all of the other bands, it's surrounded by this, albeit beautiful when you look at it through the eyepiece, smudge of nebula, which is making your photometry rather difficult. And especially if you fold in differences in atmospheric conditions, different seeing, it makes it very difficult. But anyway, from the simultaneous modeling of these light and radial velocity curves, we can determine the orbital parameters and the stellar parameters. And perhaps the first test, the most obvious test to do to see whether we're really understanding this concept of shaping of a planetary nebula by the common envelope phase is to compare the inclinations of the nebulae with the inclination of the binary. Because we've already said that the common envelope is always going to be ejected in the orbital plane, if our understanding is correct. And then that should always go on to form the waist of a bipolar nebula, because that's where the density contract, the overdensity is. And so we've done this for 9 systems so far, which doesn't sound like much, but it's enough to show this perfect one-to-one relationship, which if you do the statistics and try and check what is the likelihood of having this correlation by chance, it's less than 1 in a million. In fact, it's less than 1 in 10 million now. And the very last one of those systems we characterized last year with my master's student, James Monday. So great, that at least we've confirmed our understanding that the common envelope is always ejected in the orbital plane and makes shapes the symmetry axis of the nebula is correct. Great. What else can we find out about the process and about the common envelope phase in general? Well, through the process of characterizing these systems, we've shown that a number of these must have experienced the common envelope while they were on the red giant branch, so on the first ascent of the giant branch. And this is an important thing to know because there were some doubts beforehand, theoretically, as to whether a system that experienced the common envelope on the red giant branch would ever be hot enough, quick enough to be able to ionize the ejected envelope. Now we seem to be able to show pretty clearly that that's the case. And that's very useful because we know that the vast majority of common envelopes will occur on this red giant branch on the first ascent, just because the difference between the radius of a star on the tip of the red giant branch and the radius of a star on the tip of the asymptotic giant branch isn't that large. So the vast majority of common envelopes will occur on the red giant branch. And in fact, this is shown as well in the population of more evolved white dwarf and main sequence binaries. We also only find one early type secondary. So all of the others are late or small low mass stars, K or M type. We only find one which is solar mass or greater in the secondary stars. And this is a pretty strong indication that some of the theoretical work which indicated that the common envelope can only happen, so the runaway mass transfer will only happen when the mass ratio, so the mass of the primary compared to the secondary, is much larger, is very much greater than 1. Otherwise, the mass transfer will actually be stable and the star will manage to adjust. So this is in support of those theoretical findings. Perhaps the most exciting, I think, finding, and the one that I'm going to tie back to the simulation that I showed you earlier, is that the secondaries, the main sequence stars in these systems, are always inflated. They're always 2 or 3 times, or up to 2 or 3 times, what you would expect if you had the same star of the same mass star in the field on its own. And this is a pretty strong indication that even though during the runaway phase of mass transfer, we know that these stars can't accrete very much material because there's a strong entropy barrier between the surface of the star and the material that ends up filling its Roche lobe, that these stars have at some point experienced significant mass transfer. Perhaps not a lot of material, but at least very fast. This is a strong indication of this of accretion. And I had to put on the previous slide, I have to put this asterisk next to every, because until last year it was every, and now I found a system which doesn't follow that, because the companion is actually as big as it can possibly be. If it was any bigger, it would be transferring material back onto the companion. So it's a normal size star, but it's as big as it possibly be. And this is quite an interesting system in itself, because it means that as the system begins to relax, as the primary shrinks back inside its Roche lobe and the orbit begins to decay, there's a strong likelihood that it will begin to transfer material backwards onto the central star of the nebula. And that's interesting because not so long ago, we observed a nova eruption, which is the consequence of this kind of mass transfer onto a white dwarf inside a planetary nebula before the planetary nebula had managed to dissipate. So while the planetary nebula was still only a few tens, maybe 100,000 years old. So that means that after the common envelope phase, it was quick enough to initiate this mass transfer and experience a nova eruption. And perhaps this system is a precursor of this kind of evolution. So some more evidence of this mass transfer to support this. It comes from this system, the necklace, which I already showed you, its beautiful sinusoidal light curve. If you take a spectrum of the central star, it's dominated in this wavelength by the companion, by the low mass companion, which is an unevolved star. It's a normal low mass main sequence star. But you see that it shows lots and lots of carbon. And this star is nowhere near evolved enough to have produced its own carbon, as that happens on the asymptotic giant branch. So we know that all of this carbon-rich material must have come from the primary star, which had evolved sufficiently to produce carbon during or around the time of the common envelope phase. Yet more evidence of this accretion. So jets are a pretty strong indicator of accretion anyway. But here we can use the jets in this system, Flamin-1, to begin to tell us when this accretion happened and whether it was during the common envelope or otherwise. So if we compare models of this kind of jet ejection from binary stars, the precession and the rate at which these knots are ejected is consistent with having an orbital period for the central binary that produced them of around 100 years. But in fact, if we study the binary at the center, the period is far shorter. It's 1.1 days, 1.2 days. And so this is telling us that the jets in this system came before the common envelope phase, before the orbit shrank. So I told you that the common envelope phase acts to shrink the orbit. So we had some phase of mass transfer which produced the jets before the common envelope, and then subsequently the common envelope shrank the orbit. And this is supported again by the ages, the kinematical ages of the jets and of the central nebulae. So the central nebulae in these systems represent the ejected common envelope, while the jets trace the mass transfer. And in a significant number of these systems, we see that there's maybe 1,000 years or a few hundred years of difference between the two, indicating the jets and the mass transfer that formed them occurred prior to the common envelope, prior to the ejection of the common envelope. So we're beginning to build this picture, which says that there's a significant amount of stuff that happens before the common envelope initiates, probably some phase of semi-stable mass transfer, which is at odds with that hydrodynamic model, which I showed you at the beginning of this talk, where nothing happens before the common envelope phase because we initiate the simulation right at the start. So that might be one of the reasons why we don't successfully get the ejection in the thing, because we don't take into account the pre-common envelope evolution. Okay, so now just to show you a little bit of how useful these systems are in understanding other astrophysical phenomena, I'm going to tell you a little bit about how we've been going about finding these binary central stars and tell you a story of one of these systems. So to try and increase the number of known systems, we began a campaign to take objects which showed morphologies which should be typical of binary interactions, so things with very strong bipolarities or jets, and to observe those, target them for observations to try and show that they were binary central stars. And so this is a perfect example. Hen 2428, the cosmic butterfly I showed you at the beginning of the talk. With such a strong bipolar structure, it has to have been a binary at the center. So in 2009, I think we started looking at this system. We began observing the central star with the Mercator telescope here in La Palma. And beautifully, we've got this fantastic light curve where you see these very short, very large amplitude variations on relatively short time scales. So only on a scale of 2.1 hours, we see this vary. And that was very exciting because this would make it the shortest known orbital period binary central star yet. But there's some indications that something's not quite right here. On this plot, you can see that I've overlaid a sign fit on this curve, and you can see that it doesn't really fit that well at all. And I told you that the irradiation effect is fairly typical, typically a sine curve. So something's not quite right here, and we were very fortunate that, I mean, it sounds like a fairy tale, but it's true. We were very fortunate that during this observing run, a stray cat from the observatory decided that it would like to observe with us, and he was far cleverer than I or my co-observer Miguel Santander, OAN. And so Biff the cat knew clearly that something was wrong with our light curve, and that in fact we'd got the orbital period completely wrong by a factor of 2. The period is in fact double what we had before. And you can see that this is actually borne out when we fold it on twice the orbital period, because the minima around phase 0 and phase 1/2 are very slightly different. One is very slightly deeper than the other. So how can we understand this? We had this very simple sinusoidal shape where you have one minima per orbital period. So how can we have 2 minima and have them at different depths? Well, it turns out that this is a different kind of variability, now not due to irradiation, but instead due to one or both of the stars being so big that they fill their Roche lobe and are tidally distorted. They take on the form of the Roche lobe, looking a little bit like a teardrop. And so as we go through the orbit, we see a different amount of this teardrop. At some phases, it looks sort of spherical, and then as it's at quadrature, you see the full teardrop and it's brighter. So we end up with 2 minima per orbital period, 1 at each conjunction and 2 maxima, 1 at each quadrature. very interesting. And intriguingly, the two minima indicate being so similar, indicate that the two stars have very similar sizes and very similar temperatures, which is interesting because we know that one of these stars must be a very, very hot post-common envelope, post-AGB or pre-white dwarf star. So that probably means that they both are. And that's borne out by the radial velocities that we took using the GTC, which showed that they were almost identical masses, and in fact, very massive, both of them greater than 0.8 solar masses. So in fact, in this system, rather than having a main sequence star and a white dwarf, we have two massive white dwarfs so close together that they're tidally distorting each other, and in fact, so close together that they will merge in less than a Hubble time. Now, this is a very exciting result because, as you may or may not know, the merger of two white dwarfs, particularly if they are larger than the Chandrasekhar mass, which is the maximum stable mass for a non-rotating white dwarf, is one of the main theoretical pathways towards the formation of a type 1a supernova. And that means you get a paper in Nature and you get this beautiful press release video, which clearly contains very accurate physics. You'll see here in the explosion of what at that time was probably the strongest supernova type 1a progenitor candidate known. But we are nice enough, or perhaps stupid enough, to have shared our data with another group following the publication of our paper, and they reanalyzed our spectra. And the spectra are key in all of this because it's the spectra that give you the radial velocities, and it's the radial velocities which tell you the masses of the two stars. And so they reanalyzed in detail our spectra and noted that the very high extinction in the direction of HEN 2428 could mean that instead of just seeing absorption features in our spectrum from the two stars, one for each star, there might also be some very weak absorption features to do with that originate from diffuse interstellar bands. And you can see here they're models of these two. So basically on the left-hand side of each of these two figures is the fits to the two components without taking into account these diffuse interstellar bands. And then on the right, you can see that there's an additional very, very weak absorption feature in light blue, which corresponds to these diffuse interstellar bands. And it turns out that if you allow these diffuse interstellar bands to affect your observations, then the masses that you determine are slightly lower and in fact make the total mass less than the Chandrasekhar mass. It will still merge in less than a Hubble time, which still makes it an interesting candidate type 1a progenitor, but it's no longer the holy grail. It's no longer the super Chandrasekhar mass system, unfortunately. But nonetheless, it shows the power of these systems in hunting for these super Chandrasekhar, or at least it's hunting for double degenerate or double white dwarf systems that will merge, because these stars, as they evolve, will begin to shrink down and will no longer fill their Roche lobes. They'll no longer present this kind of photometric variability. So it means that at this phase in their lives, the planetary nebula phase, short-lived phase, they're actually easier to detect, these double degenerates, than they are later on. And that's kind of borne out a little bit by the statistics of how many double degenerate central stars we see. We find that probably this plot is not quite up to date, but roughly 20% of all of the post-common envelope or all of the binary central stars that we know show this kind of variability, which is consistent with being two white dwarfs. And in fact, the central star of Fleming 1, the one that I showed you here with the beautiful jets, is one of these double degenerate systems. And so they are excellent places to look for these. And in fact, given that they should be far more difficult to detect than the white dwarf main sequence systems where we see the radiation effect, the fact that we see so many probably means that as a fraction, there are even more. And so this could have really important implications for our understanding of populations that go on to produce these supernova type 1a. And that in itself is a very exciting thing to do, because these supernova type 1a are critical in understanding cosmology. They were extremely important in the discovery of the accelerating expansion of the universe, so much so that the people that led these kind of studies were awarded the Nobel Prize in 2011. And so these supernovae are so important cosmologically because they can be used as standard candles to measure distances. But even though we know that they are very effective standard candles, we still don't really understand their origin, systems that go on to form them, nor why they are such good standard candles. And so I think I'm coming up for time, right, if that's good. So I think
you can
add a little more. So then I'm going to jump my summary and give you a little bit of extra bonus material that I've prepared just in case I had time, and then we'll go back to the summary. So I've talked a lot about light curves, a lot about whatever. So now I want to talk about something completely different, right? So let's talk about the nebulae. When we look at the chemical abundances in planetary nebulae, we can measure them using different emission lines. And these emission lines come from different excitation mechanisms. There are collisionally excited lines and recombination lines. And so for the heavy elements, the are always far brighter than the recombination lines. So typically you use the brightest lines, the collisionally excited lines. So here in this plot, you can see some lines of double ionized oxygen at 4959 and 5007, which have fluxes relative to hydrogen beta of 150 or even higher. And then in the little inset, there are a couple of lines of doubly ionized oxygen, so exactly the same species, but with a different mechanism. So these are recombination lines, which are a factor of 100 fainter. So typically we only use the bright lines to measure our abundances. Great. But if you manage to get good enough observations that you can measure the abundances using both of these lines, it turns out that there is a strong discrepancy. The abundances from the same chemical species, but measured using lines with different excitation mechanisms, are different. The abundances from recombination lines are always higher than the abundances from collisionally excited lines. So this is a distribution of all of the measurements of this abundance discrepancy, so the ratio of abundances from recombination lines to the abundances from collisionally excited lines of all H2 regions and planetary nebulae in the literature. And you can see that there's a median discrepancy of about 2, so a factor of 2 difference, which is already pretty good, pretty big. But this extremely high tail that blasts off to 1,000 for a few systems. So if we overlay on top of this plot what these are, you can see that the H2 regions sort of cluster around the left-hand side or relatively evenly distributed. Planetary nebulae in general cover everything. And planetary nebulae with binary central stars, which are here marked in sort of light blue and dark blue, are always, almost always at least, in the very high end in this extreme tail. So this is telling us that there's something going on here in these binary planetary nebulae, which leads to this strong discrepancy between recombination lines and collisionally excited lines. And indeed, if we look at this, the strength of this discrepancy as a function of orbital period, it seems that they're all the very shortest orbital periods that have the highest discrepancies. So this is a key ingredient, again, in understanding this, this common envelope evolution and its impact on planetary nebulae. So if you go away and you take images of these systems in the collisionally excited lines and in the recombination lines, which are coming from the same species, remember, these are the same, this is doubly ionized oxygen, you see that they occupy different spatial regions of the nebula. The collisionally excited lines are more extended, occupy most of the nebula, while the recombination lines are very centrally concentrated. And the way that we can understand this is if the nebula, rather than being a homogeneous thing, contains 2 gas phases, one which has a sort of normal metallicity and one which is very metal enriched, has abundances which are much more similar to novae. And so this second metal-rich gas phase cools more effectively and ends up being brighter in the recombination lines, while the more normal gas phase has a higher temperature and ends up being brighter in the collisionally excited lines. And so how can we, so this means that this metal enriched phase is closer to the central star, so perhaps ejected later. And we can see that this happens for all. It's not just one case. These are some beautiful Muse data taken by Jorge Garcia here at the IAC, which show that in almost every case, we see this discrepancy where the recombination lines are inside the collisionally excited lines, indicating that this metal-rich component or hydrogen-poor component is centrally concentrated and probably ejected after the normal phase. So how can we understand this? Does it mean that perhaps the conclusion of the common envelope phase, which remember in our simulation that I showed at the beginning, we never managed to eject all of the envelope. At the end of the simulation, the envelope was still bound. Does this mean that at the end of this thing, there is some kind of eruptive event that manages to get rid of the very last drags of the envelope? And this means that the abundances of this very last ejection, the internal ejection, are metal enriched, be it by some form of reprocessing or eruption. Could we explain this by a fallback of the common envelope because it's not totally unbound, or by a mass transfer from the companion backwards? In any case, the simulation that we have there is not the end of the story, and it's probably far, far more complicated than we could imagine. So now I will leave you with my summary that I hope I've shown you that binaries are responsible for the formation and the shaping of some, most, all, delete as appropriate planetary nebulae, that these are really useful probes of understanding the common envelope, which is critical for understanding a number of other binary phenomena, because we know that the originators of supernova type 1a, of cataclysmic variables, of gravitational wave sources all go through the common envelope. And this is a really critical phase in which we can observe that. And that not only are they useful for studying this binary evolution, but probably it makes things even more complicated once you get to the bottom of it. And if you're interested in reading more, then I encourage, or hearing more, then I encourage you to find a copy of my book, which you can see the cover page over there. And now I'm very happy to take questions. Thank you.
Thank you, David. Thank you very much for this very nice presentation. So then maybe we can start with the questions. So if you have any question, you can also write it on the chat in case you don't have a microphone. But if you want to speak, then you can go ahead. Maybe I can start with the questions. Yeah, so you have shown that all these planetary nebulae, so they show different morphologies. Then I was wondering whether these different morphologies are due to an evolutionary sequence, so whether we are looking at different snapshots of the same process, or whether these different morphologies are produced by the different physical properties of the binary stars.
It's probably a little bit of both. We know that the shapes of these things do evolve. There seems to be some evidence that the later we see them in their evolution, the sort of more rounded they are. But that's also contaminated by the fact that these have finite visibility times, right? Because they dissipate into the surrounding interstellar medium and are no longer visible. And so there's perhaps a selection effect there in terms of older planetary nebula being rounder, because they're more likely to have come from massive single stars where their ejection, their removal of their outer layers was spherical anyway. And it's just that they've taken longer to become ionized due to the evolution of the central star, or they're visible for longer because the central star itself is hotter. But I mean, so we do know that there is some evolution there, but in principle, we don't fully understand the origins of all of the very disparate shapes that we see. And so this is one of the things that we have a bigger sample. So if I can go back to the sort of time scales of which we found these systems to give you an idea. You can see that up until about 2010, or I like to say it's until I started. So I started my PhD in 2007. So until I began working on the problem, we hardly knew anything. We only had a handful of these binaries. So it's really difficult to draw any kind of statistical conclusions. And it wasn't really until the Ogle survey doubled the number of known binaries, and then the work that I've been doing with all of my collaborators added a significant number more, that we're now in this position where if we can constrain the morphological properties as well as the binary properties, maybe we can begin to understand the processes at work in the formation of these different structures. But that's something that we're working on.
Mm-hmm. Okay. And then I have a second question. So regarding the formation of the jets, you said that these jets likely appear at a pre-phase, no, pre.
If I have this diagram again, my feeling is that probably the jets are formed when the system is a bit like this. There is probably some period at which this overflow, so when the first star begins to fill its Roche lobe, it doesn't completely run away. There's at least a few hundred years of semi-stable or non-conservative mass transfer, which mean that the system doesn't completely go into the common envelope phase, but instead manages to transfer some material onto the companion, making the companion swell up, producing these jets before something happens to trigger this runaway and the formation of the whole common envelope.
The simulations that you were referring to, do they consider magnetic fields?
The more recent ones do, yes. But again, in this, the thing happens so quickly, and because you start your simulation with the companion already on the edge, you basically ignored all of this pre-evolution where there's some material landing on there and the pre-evolution of the stars, that I don't think the magnetic field plays such a key role here, because everything happens on a dynamical timescale. I mean, there's some debate over how long the common envelope phase lasts from start to finish, but it's likely to be on the order of months to years, which is extremely fast.
Yeah. Very, very fast. Okay, we have a question on the chat from Hector Vives Arias. He says, do the processes you describe explain or give hints to the origins of the planetary nebulae that seem to show more than one shell?
Yes, so there are ways to explain that through having possible. So I've given you sort of a simple explanation of the common envelope in that it only happens once, right? In that the mass transfer is run away and everything happens in one go. There is a sort of sister theory, which is known as the grazing envelope, whereby the stars, you never plunge into a full common envelope. You have this phase of mass transfer and launching jets or something, and you manage to launch just enough of a jet that it stops the primary star from filling its Roche lobe. So you blow off enough material in the process by this grazing impact to be able to cut short the common envelope and sort of reset the clock a little bit, so it goes back to being like that. And then you end up with this a number of times. And so at each of those phases, you could feasibly create a shell or some jets, depending on how this material is lost. And so there is a possibility of forming multiple shells. There is as well, a thing to take into account is that there is significant evolution prior to this stage. So the star that fills its Roche lobe, the primary star, can already have lost a significant amount of matter as a stellar wind. And so then you have a number of winds interacting. You have the previous red giant wind, you have the ejection from the common envelope, and then finally the wind from the exposed pre-white dwarf, or the exposed core, the exposed white dwarf. And so the interaction of all of these things, as well as the advancing radiation front that goes through all of these things, can either form shells or at least give the appearance of shells, because the radiation hydrodynamics as well plays a key role in what we see. So maybe what we see isn't always tracing exactly what is there. So in fact, the formation of double shells can also be explained in a single star scenario, just that they have to be spherical because of this the play of the advancing radiation front. But it does offer a route to make all of these different crazy structures. There's always at least some hand-wavy way of making it with a binary.
Okay, thank you. Thank you, great talk. Yes, please, Elena. So do you want to ask your questions?
I try to ask. Thank you for the talk first. It's very interesting.
Thank you.
I have a couple of questions. One is related to the second part, let's say, of your talk, where you mentioned the different abundance measured on the oxygen 2 recombination rather than the oxygen 3 nebular line. And I wonder whether you have kinematic information of this region that can support the idea of a different separate ejection episode.
Exactly. This is the next step, basically, because again, if we think that this is an eruptive event that happens at the end, as I think you're getting towards, then you would expect that the kinematics would be very different, because the planetary nebula, typical planetary nebula, has expansion velocity of tens of kilometers per second, because it's just based on the interaction of these winds, mainly driven by the very slow wind. Whereas if it's an eruptive event on the surface of a white dwarf, it should be hundreds.
Okay.
There is
you're still missing this information.
So we recently got data from the VLT, some integral field spectroscopy in both the collision excited line and the recombination line of a single object. And so this is quite difficult because of the low brightness of the recombination lines. So there's only a handful of systems where we could possibly consider doing this. But we do have the data and we are looking at it now. But intriguingly, there is some work by Michael Richer in Mexico, who has been doing this in a sort of roundabout way. So not really using recombination lines from the same species, but instead using recombination lines from across species and then trying to compensate for that. And he finds that there does seem to be a kinematical distinction between these two species, but between these two gas phases, but perhaps not significant enough, or almost certainly not significant enough to support this novae-like eruption that terminates the common envelope phase. But again, the real test will be doing the same study on lines from the same chemical species, so that we really are comparing the same things. And we were lucky enough to get some data last year, I think. Not but now, the year before last, sorry, with the recent change of year, to be able to study this in one of the brightest objects in the class. So we're working on this.
Thank you. And the second question is derived from my ignorance about the common envelope. But my understanding is that a system like WU star, which are contact binary, they also form a sort of common envelope, meaning that they share a photosphere. Mm-hmm. In that case, why won't we expect an ejection?
So they share a photosphere, but the photosphere is co-rotating. It's basically as if it was a single star. The key, if I can use this here, is that so at this phase, this is almost a WU star. This is a contact binary, essentially. If the two stars were stable in this configuration, then there will be no ejection. They will continual, and there would just be radiation of gravitational waves that would change the system. The key here is that we catch this at a phase where one of the components is continuing to evolve. So the larger star on the right is continuing to ascend the giant branch. So it's still not reached its maximum radius. So it continues to overflow, get bigger and bigger and bigger and bigger, until there is material which is no longer bound to a single star, but engulfs the entire system, doesn't share a photosphere, and doesn't necessarily share a photosphere, and is non-co-rotating.
Okay.
So that's the key thing, is that we have,
clarified,
in these
yeah.
systems, we have friction in the in a normal contact binary. Then we don't really have that friction that will drive the change in orbit and the ejection of anything. Does that make sense?
A lot, thank you.
Thank you very much.
Sorry, thank you. Are there any other questions? Yes, Carmen Sanchez. So she has a question. She says, literally, I'm just letting my imagination fly, but are you aware of any common envelope theories or models involving triple systems? Could this help explaining protoplanetary nebulae with multipolar, even orthogonal jet-like ejection?
So yes, adding a third star to the system means that all bets are off. You can basically produce anything you want, right? Because triple systems are stable in certain hierarchical configurations until you start losing matter, until one star evolves and starts to lose material. Then orbits can become unstable. You can have Kozai-Lidov interactions which drive all kinds of orbital evolution, and you can force common envelopes, and you can force the ejection of stars, you can force the mergers of stars. So I mean, I'm sure Carmen is well aware that Noam Soka right now is very active in terms of saying that triples should explain a lot of planetary nebula morphologies. And if you look at the statistics of systems, then there's a reason to believe that maybe as many as 10 or 15% of all planetary nebulae, evolved planetary nebulae rather than protoplanetary nebulae, could be the result of a triple evolution. But we as yet do not have any confirmed triple central star that has survived, other than one system in NGC 246, I think it is, where it's essentially a co-moving group. So they are a triple, but they're all so widely separated that there's almost no interaction between the stars. But certainly, triple evolution could play a role in explaining a number of things. As for protoplanetary nebulae, I think we have big problems there, because I've skirted over that we think that protoplanetary nebulae are the precursors of all of these planetary nebulae, and yet, while there's at least 20% binary stars at the cores of planetary nebulae, there is as yet no confirmed binary at the heart of a protoplanetary. And it might be because they're more difficult to find, or it might be because we're not really understanding things completely, and the evolution from protoplanetary to planetary is not as obvious as we think.
Mm-hmm. Thank you. Thank you, David. She says, excellent talk.
Thank you.
Okay. Are there any other questions? No. Then in that case, thank you very much, David, for this great talk. And then see you all next week for a new CAP seminar. And take care.
Thank you.
Thank you,
Take care,
David.
everybody.
Take care. Bye.